Tonight, we are going to follow one small sentence to the edge of the largest library ever assembled. The sentence is not famous. It does not explain a law of physics or record an important election. It is simply a careful human observation about an uncommon thing. Perhaps it describes the sound made by ice beneath an old wooden bridge. Perhaps it records a word used by only a few families. Perhaps it explains why a machine failed in a way that its designer had never seen before. To a person, it may feel ordinary. To a future artificial intelligence, it may be one of the last examples of its kind. We will see how such a sentence enters a training collection, how it is broken into tokens, how it becomes a tiny adjustment inside a model, and how it can disappear when one generation of machines learns too carelessly from another. We will also see why synthetic data is not simply artificial pollution. Used with provenance, selection, and a reliable way to check answers, it can become a kind of curriculum. There is no single night on which humanity runs out of data. The internet will not suddenly become an empty shelf. The real question is quieter. At what point does another copied page teach less than a genuinely new observation? And when that point arrives, where will the next lesson come from? You do not need to remember every term. The details can pass by like lights beyond an observatory window. For now, it is enough to imagine the sentence waiting at the edge of a vast library, while context moves slowly between the shelves. Chapter 1. A sentence at the edge of the library. Before a model can learn from a sentence, someone or something must first preserve it. That sounds obvious, but it is the beginning of the entire story. Human knowledge does not appear in the world as a neat collection of training examples. It appears as conversation, gesture, measurement, argument, repair, mistake, memory, image, rhythm, code, and silence. Only a portion becomes recorded. Only a portion of that recording becomes digital. Only a portion becomes accessible. And only a portion survives the many filters between a public document and a model's training run. Our rare sentence might begin in a field notebook. Later, it may be typed into a small website. A search engine may discover it. An archive may preserve a copy. A large collection may download the page. Then a sequence of tools may remove menus, advertisements, repeated headers, malformed characters, and suspected spam. Every step is reasonable. Every step can also remove something. A filter designed to favor polished prose may reject regional language. A deduplication system may decide that two similar warnings are redundant, even if their small difference contains the important lesson. A quality classifier may prefer the confident voice of an encyclopedia to the uncertain note of a mechanic who has encountered a new failure. This is the first reason that the size of the internet is not the same as the size of a useful training set. 1 trillion copied pages do not contain 1 trillion independent observations. A repeated sentence can make a collection larger without making it wiser. Conversely, one unusual but accurate record may add something that no amount of repetition can replace. When the selected text reaches a language model, it is divided into smaller pieces called tokens. A token may be a whole common word, part of a rare word, a mark of punctuation, or another learned fragment. During training, the system repeatedly tries to predict what comes next. Its prediction is compared with the actual token, and a learning process makes countless small changes to the model. The model does not place our sentence on a shelf and retrieve it in the ordinary way. its influence is distributed. It becomes part of a landscape of probabilities, which ideas tend to occur together, which patterns follow other patterns, and how language behaves in many different contexts. Common patterns press on that landscape again and again. Rare patterns touch it lightly. They can still matter. They can influence how the model responds when it encounters a similar situation. But their survival depends on representation, capacity, training choices, and the many other examples surrounding them. So our sentence begins its journey with a fragile status. It is real, it is useful, it is also quiet. The coming question is not merely how much text a machine has read. It is whether the training process preserves the shape of a world in which unusual events, small communities, and improbable but important details still exist. Chapter 2: How the Web Became a Training Set. The early web was not built as a textbook for artificial intelligence. It was built page by page for people. Universities published papers and course notes. Governments released reports. Programmers discussed bugs. Volunteers built encyclopedias. Businesses described products. Families posted recipes. Forums preserved questions that were too specific for a manual. The result was untidy, duplicated, multilingual, contradictory, and extraordinarily rich. For machine learning, this disorder became an opportunity. Instead of asking people to label every sentence by hand, researchers could train models to predict parts of the data from other parts. A text could provide its own training signal. Remove or hide the next token, ask the model to predict it, then compare the prediction with what the writer actually wrote. At large scale, this simple task contains many hidden lessons. To predict the next word in a legal argument, a model benefits from patterns of law and logic. To continue code, it benefits from syntax and common programming structures. To complete a description of a journey, it benefits from place names, sequence, and ordinary expectations about the world. This does not mean that prediction is identical to understanding in the human sense. It means that accurate prediction across diverse text rewards a system for building useful internal regularities. As models grew, training collections grew with them. Books, reference works, websites, code repositories, discussions, and other corpora were mixed in different proportions. The exact contents of many commercial datasets are not public, and the boundaries involve technical, legal, and ethical questions. Still, the broad direction is clear. More capable systems were often supported by more computation, more parameters, more data, and better procedures for selecting and using that data. But the public web is not a clean reservoir. The same article may appear at many addresses. A quotation may be copied thousands of times. Automatically generated pages can create enormous volumes of nearly empty variation. Some material is inaccurate. Some is private when it should not be. Some is copyrighted or licensed under terms that matter. Some is dangerous to collect. Some is simply irrelevant to the capabilities a trainer wants. Training, therefore, begins long before the first processor performs the first matrix multiplication. It begins with decisions about collection and exclusion. Those decisions create a hidden curriculum. Suppose two datasets contain the same number of tokens. One contains many copies of popular material. The other contains fewer repetitions, more carefully selected technical explanations, broader language coverage, and records of rare but valid cases. Their token counts may match, while their educational value differs greatly. This is why the phrase human data can be misleading. A careless comment and a careful proof are both human. A copied marketing page and a unique maintenance log are both text. The useful distinction is not merely human or synthetic. It includes quality, diversity, relevance, provenance, and whether an answer can be trusted. Our rare sentence survives only if the collection values something beyond frequency. It needs a process that notices the quiet edges of the distribution, not only its bright center. And now, beyond the shelves, another constraint appears. Even a magnificent library must be read with a finite amount of time and energy. Chapter 3. The Arithmetic of Scale. Imagine a training run as a journey with a fixed budget. Computation is the distance the system can travel. Model parameters are part of the capacity of the vehicle. Training tokens are the road beneath it. If one part grows while the others remain poorly matched, resources can be wasted. Research on compute-optimal language models made this relationship especially visible. In the study commonly associated with the model chinchilla, researchers examined how model size and the amount of training data should scale under a fixed compute budget. Their results suggested that several large models in the comparison had been trained on too few tokens for their size. The useful lesson is not one permanent ratio. Architectures, objectives, data mixtures, and optimization methods change. The lesson is that a larger model does not automatically become a better model if the training process cannot provide enough useful learning. This created a natural appetite for more data. Yet counting available tokens is difficult. Should duplicated text count? What about low-quality pages? What about languages that current filters handle poorly? What about books and databases that exist but are not licensed for a particular use? What about audio, video, scientific instruments, or private records that could be transformed into useful representations? Estimates of data scarcity are therefore estimates built on assumptions. They can describe plausible pressure, not announce a universal expiration date. There is another complication. A model can see the same token more than once. A training system can repeat high-quality data over several passes. It can change the order, create related tasks, or focus on material that remains difficult. The value of an example is not exhausted in precisely the same way that fuel is burned. But repetition has limits. If the model already predicts an easy, common pattern with great confidence, another identical example may add little. Progress begins to depend on material that is new, difficult, precise, or arranged in a more useful curriculum. This changes the meaning of scale. The first era of web-scale learning could treat collection as expansion. Find more pages, clean them, and train a larger system. A later era must treat data as design. Which concepts are missing? Which languages are underrepresented? Which mistakes does the model continue to make? Which examples reveal a boundary rather than repeat the center? Our rare sentence becomes more valuable in this later era. Not because rarity alone creates truth, but because it may contain information that the model cannot obtain from common examples. The deepest scarcity is not a shortage of symbols. Machines can generate symbols without end. The scarce resource is a connection between symbols and something outside the generator. A human intention, a measured result, a proof, a successful repair, a failed experiment, or an event that really happened. There is also a geography hidden inside the arithmetic. The public web is not evenly distributed across languages, regions, professions, or ways of life. Some languages have billions of accessible words. Others have small digital archives, inconsistent encoding, or very little material that can be licensed and processed. A global token count can rise while the available evidence for one community remains almost unchanged. Translation helps, but translation is not a perfect substitute for original expression. A translated story can preserve its central meaning while smoothing local ambiguity, humor, rhythm, or social context. Automatically producing more translated text can improve access, yet it can also multiply the interpretation of the translating system. The output is useful, but it is not identical to a new witness speaking from within the language. This creates two different kinds of scarcity. There can be too little material for continued general scaling, and there can be too little representation of a particular part of the world. The second scarcity may remain even inside an apparently enormous dataset. Careful trainers can respond with multilingual collection, community partnerships, better tokenization, and evaluation designed by people who know the language. These methods are slower than indiscriminate scraping. Their slowness is part of their value. They turn collection from extraction into a relationship. Once this distinction is clear, an infinite synthetic library begins to look less like an infinite source of knowledge. It may be an infinite hall of mirrors. Chapter 4. When the library contains copies of itself. Long before generative AI, the web already contained automation. Templates created pages. Feeds repeated stories. Search-oriented systems produced variations of similar text. Generative models greatly increase the speed and fluency of this process. A machine can now draft an article, summarize another article, rewrite the summary, translate the rewrite, and produce thousands of related pages. Some may be useful. Some may be corrected by people. Others may retain a small error and carry it forward with a smoother voice. If future training systems collect the web without reliable provenance, they may encounter growing amounts of material generated by earlier systems. The new model then learns partly from the projection of its predecessors. The simplest version of this feedback loop works like a copying game. Begin with a distribution of real examples. Train a model. Sample a new collection from that model. Discard the original collection. Train the next model only on the new samples. Repeat. Even if each generation is reasonably good, it is not a perfect copy of the original distribution. Sampling introduces chance. The model represents some patterns better than others. Approximation introduces error. When a rare event is missed in one generation, the next generation may never see it. This is the setting in which researchers describe model collapse. The term can sound dramatic, as if a model suddenly stops working. The observed process can be more gradual. Early collapse means losing parts of the tails, unusual names, uncommon combinations, minority patterns, and low-probability events. The center may remain fluent for a while. Later, variation can shrink further, and the learned distribution may become a poor image of the original world. Our rare sentence is especially vulnerable. It may be represented only weakly in the first model. When that model generates a replacement dataset, the sentence's kind of observation may not appear. The second model cannot preserve evidence it never receives. After several generations, the library may still be enormous, but one of its windows onto reality has closed. The Nature paper that gave model collapse broad attention studied recursive training in several kinds of generative models. Its central warning was about indiscriminate use of model-generated content and the loss of information about the underlying distribution. But a warning is not a prophecy. The experimental setup matters. Replacing original data is different from preserving it. Unfiltered samples are different from verified examples. A model generating prose about the open world is different from a system generating a geometry problem whose answer can be checked. The hall of mirrors becomes dangerous when the mirrors are mistaken for windows. If the training system knows which is which, synthetic material can play a more careful role. Provenance is the label on the frame. In a perfect archive, every item would carry a trustworthy account of where it came from when it was created, whether a machine transformed it, which source it summarized, and what permissions govern its use. The real web rarely offers this perfect history. Files are copied, metadata is removed, paragraphs are combined. Human and machine work can be interleaved in the same document. Detection based only on writing style is unlikely to provide a permanent answer. Generators change, people edit their output, and human writing itself covers a wide range of styles. A classifier may offer a probability, but a probability is not a chain of custody. More reliable provenance may require information recorded at creation, agreements between publishers and model builders, durable content credentials, or controlled collections whose history is known. None of these measures will cover the entire internet. They can still create islands of higher confidence. Deduplication also becomes more subtle. Exact copies are easy to identify. Near copies may differ in formatting, translation, summary, or a few important facts. Removing too little allows repetition to dominate. Removing too much can erase legitimate variation. The correct boundary depends on the purpose of the dataset. A future training collection may therefore preserve several layers: an immutable archive of original material, a map of transformations, a curated curriculum, and a synthetic practice set. The layers can interact without pretending to be the same. Chapter 5: The Quiet Loss of Rare Things. To understand why the tales disappear first, imagine a night sky represented by a collection of observations. Bright, common stars appear in many records. If a few records are lost, the stars remain easy to reconstruct. A faint object observed once is different. Remove that one record and the object vanishes from the collection, even though it remains in the sky. Probability distributions also have centers and tails. The center contains common events. The tails contain events that occur less often. Rare does not mean unimportant. A severe engineering failure may be rare. An unusual interaction between medicines may be rare. A language spoken by a small population is rare in a global corpus. A creative idea may be valuable precisely because it is not the most probable continuation. Generative models are often asked to produce plausible samples. Plausibility tends to favor patterns the model has learned well. If these samples become the next generation's entire training world, uncommon patterns receive fewer opportunities to survive. There are at least 3 kinds of loss to keep separate. The first is sampling loss. A finite generated collection may simply fail to include an uncommon case. The second is approximation loss. The model may not represent every detail of the original distribution equally well. The third is functional limitation. The chosen model and training objective may be unable to express some structure, even when examples are present. Across recursive generations, these errors can compound. The result is not necessarily obvious nonsense at first. A model may sound polished while becoming less sensitive to unusual reality. It may answer common questions well and fail precisely when a user brings an uncommon but legitimate need. This is why diversity is not only a social decoration added after training. It is part of informational accuracy. A system that models only the statistical center does not model the whole world. The same issue appears in creativity. If generated material is repeatedly trained on generated material, styles can converge toward patterns that are safe, familiar, and easy to imitate. The output may remain attractive while becoming narrower. Variation can disappear before fluency does. Our sentence about ice, language, or machinery is a small defense against that narrowing. It says that the world once surprised a person in this particular way. Its value is not that every model must repeat it. Its value is that the possibility remains represented. To preserve such possibilities, future datasets may need explicit attention to the tails. Trainers may measure coverage, preserve original collections, track provenance, and deliberately seek examples from regions where the model is uncertain. The objective changes from making the most typical answer slightly more typical to making the model's picture of reality less incomplete. One practical method for finding incompleteness is active learning. Instead of collecting everything first and asking questions later, a learning system identifies cases about which it is uncertain or where models disagree. It then requests a label, an experiment, a demonstration, or a more authoritative source. The next unit of data is chosen because it is expected to resolve a gap. This resembles the way a careful student studies. Reading another explanation of a familiar idea may feel comfortable. Working through the exact step that remains confusing provides more information. At large scale, uncertainty is difficult to measure. A language model can sound confident where it is wrong. Disagreement can reflect noise rather than productive doubt. Human experts are limited, and asking them to review endless machine questions can become another form of invisible labor. Still, the principle is valuable. Data quantity becomes secondary to information gain. A single verified counterexample can matter more than 1,000,000 easy continuations. Evaluation sets can guide this search, but they too must evolve. Once a benchmark is widely optimized, success on it may reveal less about performance beyond it. Private or newly created evaluations can test generalization, while domain experts can describe failures that generic scores overlook. Our rare sentence might enter the curriculum precisely because a model failed near its subject. The failure becomes a request for evidence. The evidence becomes a correction, and the correction is preserved with enough context to remain useful after the immediate test has passed. Chapter 6. Synthetic data done carefully. Synthetic data is not one substance. It can be a careless imitation of ordinary web text. It can also be a carefully constructed exercise, a simulated rare event, a reformulation of verified knowledge, or a problem whose solution is checked by a separate system. Consider a teacher preparing practice questions. The teacher is not discovering new mathematics with every worksheet, yet the worksheet can help a student learn. It selects a concept, varies the surface details, orders the difficulty, and provides many chances to apply a rule. Synthetic data can perform a similar function. The Phi-1 research project, described in textbooks Are All You Need, combined selected web data with generated textbook-like material and exercises for code. The important point was not that generated text is magically superior. It was that a smaller model could benefit from data designed around educational quality and the skills being taught. Other instruction tuning methods have generated candidate instructions, removed duplicates or invalid examples, and trained on the filtered result. Here, generation expands a curriculum. Filtering tries to prevent expansion from becoming noise. There are several ways synthetic data can help. It can balance a collection by producing additional examples of a known, verified pattern. It can transform one explanation into questions, counterexamples, and step-by-step exercises. It can create adversarial cases that expose a model's weak points. In simulation, it can produce situations that would be expensive or unsafe to collect in the physical world. But synthetic data cannot give more truth than the process used to create and check it. If the generator has a misconception and no verifier catches it, multiplication amplifies the misconception. If the prompt asks only for typical cases, the curriculum may become narrow. If generated examples replace original evidence, the system can lose the reference point needed to notice drift. This is why research distinguishing replacement from accumulation matters. Work on recursive training has found that the collapse seen when synthetic generations replace original real data can be avoided in tested settings when original data is retained and synthetic data accumulates alongside it. That does not prove that every mixture is safe. It demonstrates that the slogan "synthetic data causes collapse" is too simple. A more accurate rule is this: generated practice is most useful when the underlying knowledge remains anchored, the purpose of each example is known, and quality can be evaluated. Our rare sentence should therefore stay in the library. Synthetic examples may build variations around its lesson, but they should not erase the record that the lesson came from a human encounter with the world. Chapter 7: Teachers, Judges, and Verifiers. Some domains make synthetic learning easier because they provide a judge. In a board game, the rules define legal moves, and the final position identifies a winner. AlphaGo Zero learned through self-play without relying on a collection of human games. It could generate its own experience because the environment supplied clear feedback. Geometry offers another kind of judge. A system can propose constructions and proof steps, while symbolic tools check whether deductions follow. Alpha geometry used synthetic problems and a symbolic deduction engine to build capability in a constrained domain. Code can sometimes be executed. Equations can sometimes be checked. A theorem can sometimes be verified by formal rules. A simulated robot can receive a score for reaching a target without collision. In these settings, synthetic data is connected to an external test. Open-ended language is harder. If a model writes a confident paragraph about an obscure historical event, fluency does not verify the event. Asking a second model may help, but if both learn the same error, agreement can create false comfort. Future training systems may therefore separate several roles. A generator proposes examples. A critic searches for weaknesses. A tool checks calculations or retrieves evidence. A human reviews uncertain or consequential cases. A provenance system records where the underlying claim came from. The final training example carries not only an answer but a history of why that answer was accepted. This resembles a scientific process more than passive reading. The distinction between teacher and witness becomes important. A teacher can rearrange established knowledge into a useful lesson. A witness contributes new evidence about the world. A model can often help with the first role. It cannot, by language alone, guarantee the second. Our rare sentence was written by a witness. Perhaps that witness was an instrument, a worker, or a community preserving its own vocabulary. Synthetic systems can create exercises around the sentence. They can translate it, compare it, and test whether a model notices its implications. But the original connection to reality remains special. As easy web-scale expansion slows, the design of these checking systems may matter as much as the size of the generator. The valuable data set of the future may not be the largest pile of text. It may be a smaller collection in which every difficult example carries evidence, uncertainty, and a reliable route back to its source. Chapter 8: Beyond the Public Web. If passive web text offers diminishing returns, learning does not have to stop. The world contains more information than the public web can express. Scientific instruments produce measurements. Software tools reveal whether actions succeed. Robots encounter friction, weight, distance, and delay. People correct assistants during real tasks. Organizations hold specialized records that may be useful under careful agreements and privacy protections. Each source introduces new possibilities and new responsibilities. Licensed collections can provide high-quality material with clearer provenance. Private data partnerships can also concentrate power and create risks if consent, security, and purpose are poorly defined. Interaction data can reveal real user needs, but it can also expose personal information. Sensors can ground a model in physical events, while carrying the biases and limitations of the instruments. Simulation offers a middle space. A system can practice millions of variations before touching the physical world. Yet a simulation is a theory encoded in software. If the theory omits an important effect, the learner may become excellent inside the simulation and surprised outside it. The remedy is not to reject simulation. It is to return regularly to reality. A robot trained in a virtual warehouse can be tested in a real warehouse. The difference between expected and observed behavior becomes new data. A scientific model can propose an experiment. The measured result can support, refine, or reject the proposal. A coding agent can attempt a change and read the actual test output. This creates a different learning loop from recursive imitation. Instead of model, sample, the loop becomes model, action, observation, correction. New information enters from outside the model. This may be one of the most important changes in the next era of artificial intelligence. Progress could depend less on finding another enormous undifferentiated scrape, and more on building systems that know how to ask useful questions of tools, people, experiments, and environments. That future is not guaranteed. Experiments cost money and time. Physical systems can cause harm. Access to high-quality feedback may be unequal. Privacy and ownership remain difficult. A measured result can still be misinterpreted. But the direction clarifies the original puzzle. AI does not need an infinite internet. It needs continuing contact with evidence. Chapter 9: A future that still needs witnesses. We can now return to the sentence at the edge of the library. It survived because someone noticed something, someone recorded it, and a training system treated it as more than disposable noise. It entered the model as a small influence among billions of other influences. Later, when synthetic pages filled the shelves, the original record remained available. A careful system marked its provenance. It knew that generated exercises were practice, not new witnesses. It used verifiers where verification was possible. It preserved uncertainty where certainty was not possible. And when the model encountered a related event, it could recognize that the common answer was not the only answer. This is a calmer picture than the idea of AI suddenly running out of data. There may be scarcity, but it is not the scarcity of text-shaped objects. Those can be produced without limit. It is the scarcity of trustworthy novelty, observations that add something real, corrections that reveal a mistake, and examples that represent parts of the world the model has not learned well. Synthetic data will probably remain part of the solution. It can organize lessons, extend practice, expose weak points, and make rare scenarios easier to study. Human data will also remain important, especially when human experience is the subject. Tools, formal systems, simulations, and sensors can add other kinds of feedback. The best future training systems may combine all of them while keeping their roles distinct. A generated answer should not silently become evidence for itself. A simulation should not be confused with the world it approximates. A popular pattern should not erase a rare truth. A private interaction should not become a public resource without permission. There is an economic change hidden here as well. During the age of abundant public text, the expensive objects were models and compute. Data often appeared to be a raw material waiting to be collected. As generic text becomes less differentiating, verified experience can become the scarcer asset. A laboratory that can run reliable experiments, a software platform that observes real task outcomes, or a community that maintains a trusted archive may contribute something that cannot be reproduced by asking a model to speak for longer. This does not mean that every private database becomes good training material. Records can be biased, incomplete, invasive, or gathered for a purpose that does not justify reuse. Value and permission are separate questions. A dataset can be commercially valuable and still be inappropriate to use. The strongest systems may therefore need governance alongside engineering. Contracts, access controls, audit trails, deletion procedures, and ways for people to understand how their contributions travel. Better data practice may look less like mining and more like stewardship. Stewardship is slower. It asks who created a record, what it means, what can be learned from it, and when it should be removed. But when another trillion unexamined tokens offers little improvement, careful stewardship stops looking like an obstacle. It becomes part of the training technology. And a model should not be judged only by how smoothly it describes the center of experience. It should also be judged by how honestly it handles the edges. In the Midnight Observatory, context closes the synthetic volume and leaves the original notebook open. The two books are not enemies. One contains a record, the other contains practice. Between them lies a small instrument that can test what is true. The library of the future may be smaller than infinity and still be enough. It may grow more slowly and learn more carefully. Its most valuable new page may come not from another machine rewriting what is already known, but from a person, a tool, or an experiment returning with news from beyond the shelves. For tonight, the rare sentence remains where it can be found. The lights over the archive grow dim. The repeated copies fade into the background. One amber signal marks the original observation, and then even that light becomes soft. There is nothing more you need to hold on to. Good night.